Hi, this is Chong Kim. Welcome to Ruby Chess version 4 part 2. Okay, let's run the RSpec, see where we left off. Okay, so it takes like 0.06 seconds. So let's take a look at some ways that we could speed this up. So first, let's modify the gem file to include ruby-prof. This is the profiler. And we run bundle so that it includes it. And let's go and edit the spec. And we're going to require the ruby-prof. Okay. So when it's reading the file, let's start the ruby-prof, the profiler, and at the end, we're going to stop it. We're going to pass this into ruby-prof one of its printers. I think the basic one is flat, the flat printer. So we'll create a new instance with the result, and we're going to print it to the standard out. Okay, so we should have everything set up, so we can go and check. So this is going to take a little bit more time because it's collecting all the diagnostic information. This is interesting. It spent the most amount of time in bounded. So let's take a look at bounded. Oh, wrong file. Okay, let's run the C tags. So everything's up to date, and let's go to bounded. So let's see where bounded is being used. So it's used in one place, and so it's probably used a lot, and so it's the overhead is, so there's nothing in this function that looks like it can be optimized, but the fact that it's done so many times, it's probably the function call. So what we can do is just remove it and inline this, because this is only happening in one place, and replace all the indexes with from, and we can get rid of this. So let's see if this makes any improvement. So the total time it ran was for about 5 seconds. So let's 5 seconds, 5.25 seconds. So we run this again. So it made a little bit of difference, quite a bit. Okay, so let's take a look now. So find is now the biggest part. So find was 11%, and now it's 13%. Well, it's 13% because we got rid of the bounded. Okay, so let's take a look at find, and another thing to look at is move. So find, move, find, repeat. There's nothing we can do about white. And this is called quite often. So it looks like we should focus on these three things: find, move, and find, repeat. Okay, just looking at some of these others. String include. Okay, so even if we fix some of these things, it's probably not going to make that much of a difference, so we'll just leave those alone. Okay, so let's take a look at find. Okay, find is right here. Okay. So one thing we can see immediately is that these functions, they're not using color and list. Color and list is only used for the pawn, so we might as well just take this out and put it directly in here. So it only gets used when it's a pawn. Okay, and we don't need to return the list, which means we don't need to assign it. This will just return find repeat. Okay, so this simplifies the code. And oh, and another thing too is, since we know it's a pawn, we can just test it to see if the piece is a capital P. If it is a capital P, then it's white. Okay, so this also simplifies the logic here as well. Okay, let's see if there's any other. Doesn't look like there are any other places that we can optimize. So this looks like it may be it. So we'll save and we'll just see how it goes. So it made some improvements, 3.86. So find is number 2. Move is now moved up 1. So let's take a look at move. Okay, so we're in move. Here it is. Okay, so let's see if there's anything that we can do here. So we have a list. We're going through. Still need to do all of these things. Here's one area that we could probably improve. We're creating a copy of the position, which means copying the whole board. And the board is 10 by 12, so that's 120 elements in the array, which means there's 120 strings that it has to allocate. So that's quite a bit. So at least 120. So this dupe is a little expensive. So instead, let's actually make the change on this position. We'll get rid of the temp after we get this working. So what we can do is we can make the move and then undo the move. So I'll just set this to be is in check, and then return not is in check. In here, we're going to reset this, so the board 2, actually board from, is going to be put back with board 2, and board 2 is going to be the whatever piece it was. So let's store that. So the temp piece is going to be the temp board 2. Okay. The other thing too is we have to turn the switch. Okay. So temp king. Okay. So let's just assign this. So temp king is equal to whatever previous value, and then we'll reset it back. So we'll say the temp king turn is equal to whatever we stored it. Okay, so we stored this, so everything should be back to normal. And we're pretty confident about making these changes because if there's any problems, then the test should pick it up. Okay, so we save and run the RSpec. Okay, so that saved about 10%. So it was 3.86 seconds before, and now 3.6. So if we run it again, it should be close. 3.7. So there's a bit of variability. So it's good to run this a few times just to get an idea. And they should be fairly close to each other. Okay. So let's see what the next item is. It's still move. Move is still up there. Let's see if there's any more things that we can do. So we have the select. And everything else in here seems like it's necessary, and there's not a lot you can do. The problem with Ruby, using Ruby as a language to do something computationally expensive like this, is that you're not able to manipulate the memory management and control how things are executed. So so it is slower. And if you saw my previous screencast about using C, the C extension to Ruby, you'll notice that it was about 7 times faster using the same algorithm. So so right now, it's a little bit. This program is a little bit slow, but that's not really because of the algorithm. I think it's mostly because of Ruby. Um, okay, so let's see. Okay, so let's take a look at. Let's see. So let's take a look at uh, find repeat. So in find repeat, okay, so you have all these directions. See list. Okay, so there doesn't seem like there can be any significant speedups that we can do. We could do some minor speed up, but like for example, we could inline these white um, and have if conditions. So, but that would make this code less readable, and it probably wouldn't make a difference in terms of speed. So I think we're pretty much done with the optimization. Let's see. Just let's look through this code, and pretty much, yeah, I don't see anything really sticking out. Okay, so let's go to the next part, which is to let's see. Let's write a new feature called possible moves. Okay, so see, a good place to have it is right here, right before. Well, actually, we could do it right after move. So actually, let's take a look at what happens if we take out the profiling now. So I'll just comment this out so that way later on, if we wanted to, we want to use this, we can just uncomment it. Okay, so let's run the RSpec, and I think it was 6.8 seconds, and now it's, I mean, 0.6 seconds before, so now it's 0.4 seconds, so less than half a second. If we run this again, it seems pretty consistent that it's less than half a second. Okay, so this is pretty good. All right, so let's add a new function, possible moves. Okay, so let's start off with setting up a position. And set the board to be okay. We just set this up right now, so it's a little bit different than before. It takes a little bit more effort to create the grid. Okay, and we need 4. Let's see. Okay, so this should be good, and we start this off with rook, knight, bishop, queen, king, pawn. Rook, knight, bishop, queen, king, bishop, knight, rook, and we have to put those borders in. And actually, this we're just setting up the possible moves. So okay, so we have an empty grid here, and let me see, what else do we need? Okay, so let's just say that we have a rook here. Actually, instead of setting it this way, let's just set it up so that we give it the coordinate positions. All right, so the rook is going to be on e4, and the white king. Okay, actually, let's just put a rook there and just say possible moves. Okay, it's white's turn, and okay, this is going to be in the coordinate notation. So e4 to e8 and so on. So right now we'll just do this. It'll be wrong, but at least it's a start. So we'll set this up so that it compiles when we save now. Okay, we're missing something here. Okay, we have too many parentheses. Okay, wrong number of arguments to the constructor. So let's go to the constructor. All right, so ops is equal to empty. So if any of the keys if the size is equal to 1, then we will set the board to be actually nils, and there's 12 by 10, so there's this many nils, and this is the else part. Okay, and we can just end this, and we can go through each of them. So ops each, so we have the piece as the key and the index position where it's located. So and we only want to go through the keys if the piece size is 1. Right? Oh, actually, we want to skip it if it's not equal to 1. And okay, so now we know that it looks like something like this. So we can set it now. So the board's index position is now the piece. Okay, so that should go through and set up the board. And we might as well set up everything else too. So for example, the turn, it should be the ops turn defaulting to white. Same thing for the castling. Defaults, ops, en passant, ops, half move, ops, full move. And for the king, we're going to do it differently. We're going to actually look for it. So that the easiest way to do that is use index. Index will look for, the king would be capital K for white king, and for black you're looking for the, so at board index of the lowercase k. Okay, and I believe let's actually check. So in pry, if I have a string and I say index of a x, that should give me the index position, so it's 0. But if it's something that's not there, it returns nil, so I'm okay. So okay, so everything looks good. Save. Undefined method, possible moves. Okay, so this is good. So we have the setup and the possible moves. Okay, so let's just return empty, make sure that, okay, all right. All right, so let's think about how the possible moves should look like. Okay, let me do an RI on index, on array index. Okay, so array index takes just an object. Okay, because I was actually for some of you may try to say RI array index like this, and it may not work, and that's because um, when you install Ruby, it doesn't come with the documentation. So there's another gem. I think it's called rdoc data. Yes, rdoc data. So if you just do a gem install of rdoc data, then you should have the the documentation for all the core classes. Okay, let's see. So possible moves. Okay. All right. So what I actually wanted to do was to find all the locations for uh, for an element. So let me go back to pry. So for example, if I have hello, there are two L's in there, and if I say index of an L, I don't want it to return 2. I want to return a list of 2 and 3 because that's where the L's are located. So let's take a look at an array and see if there's anything that might be what I'm looking for. So I see there's index here, but that's not what I want. There's find index, so maybe find index. So Ruby core find index. It gives the, it looks like it's probably the same as just index because it's giving me the documentation for index. Oh, okay, so it doesn't seem like there is any. Okay, so I probably have to go through and look through it myself. The reason why I wanted to look for it using one of those methods is because it would be faster than iterating through because Ruby is not very quick about it. So let's just go through the whole list looking for each of the elements. So we need to start from 0 through 7. Actually, it might be a good idea to, well, we can make it into a list. Actually, we'll create a list and we'll return the list. Okay, and 0 through 7 again. And this would be the see, I'll just say I, and this will be J. So we need to calculate what the index position would be. So we know for if this is the column, we have to add 1 because we have a border. And for the row, we have to multiply by 10. And we are skipping 2 rows because it's padded by 2. So this should go through all of the positions, and we can look for the pieces. So let's see. So the pieces would be depends. If you're white, you're looking for rook, knight, bishop, queen, king, pawn, capital. Otherwise, rook, knight, bishop, queen, king, pawn, lowercase for black pieces. Okay, so we have a piece, and one thing that we need to know is their direction. So we can try to use find piece that's able to go to this location, the index. And this will give us a list. And let's just add it to the list. So list dot append. Okay, I'm not 100% sure about that. So let's just see if the list is 1, 2, 3, and we say list dot append 4, 5. Okay, so if it's not append, then it's probably plus equals probably. No, actually, plus equals is probably it. Okay, and list is changed. So there's no append. Okay. All right, so this should do it. Each for string. That's because we have to say cars. Okay. Oh, these are all the interesting. Okay, so it gives us the starting position. But what we really need to do is we need to map this. So map this index would represent the to location. And we're looking for the from. So okay. So we have a list of froms. And so what we need to do is say from to. Okay. All right, so let's see. Saving. All right, so this is more like it. So we see that these are all the possible positions that it can go, and we see that 65 to 25 is one of them. So this looks good, so we can take this. Let me see if I'm able to copy that and go back and paste and just replace this with this. Okay. All right, so we have possible moves for rook, and it's a pretty good time. Let's say that, okay, so let's try another piece. Since we're using a function find, which has already been used and tested, we don't have to make this an exhaustive test. So I'll just put this as, actually, I'll just change this test so it'll just run in one line. So the way it would be is, it expect position new rook on e4 dot possible moves to equal this. Okay, and closes. Okay, good. So I'll just copy this and say a bishop, and it'll give me something different and expected but got this, and this should be the correct one, and we'll replace it here. Okay. Okay, so now we have everything passing. Okay, so we have the possible moves, and okay, so we can start working um, on the algorithm for the A-star algorithm. Okay. Okay. So one of the things that we need to do is okay. So let me explain how the A-star algorithm differs from the minimax that we did in the previous version. In minimax, you have a node, and it branches out. Okay, and then you have another node, and it branches out like this. And because this is a chess program, the branches are not 2, but it'll be like 10 or something like that. The problem with the minimax version is that it's depth first. So it starts from the top, goes down to the next level, and it goes down to its children. And goes down like this. Like this. And let's see. And it has to go to some type of terminal node. So I'll use these stars as terminal nodes. So it has to get to the bottom in order to calculate the parent node, and then the parent node from here, and so on. So it starts from here 1, 2, 3. Oops, 3. Then it goes here 4. Actually, it doesn't evaluate this, so it evaluates when it gets to here. So this would be the first evaluation. Then it goes to here. That's the second evaluation. Then this gets evaluated. When it goes up, it goes down, and it has to go down to its to the terminal nodes again. So on. So I'll just use it like this since we're running out of space. Like this. So, and you can see the problem already that for a game like tic-tac-toe, you can go all the way to the bottom. But for a game like chess, the bottom is just too far. And so you have to put some type of limit. So normally you would put a limit of, let's say, 4 plies or whatever. But it still takes quite a long time, and it's not very efficient in the way that it's searching, because it has to go in order to do a good search, it has to do a complete full search of all of the 4 levels. The reason is because if you don't, then you have nodes that are completely overlooked. So if I only had time to, let's say for example, I said only look at 4 nodes, evaluate up to 4 nodes. So I would start here, end up doing these, but these would be ignored. So I may have a whole bunch of these, but these are not looked at all. So the way the A-star algorithm works is you start with a node. So it starts very similar. And you take a look at its children, like so. Okay, so you replace this with the children. I'll put a dash. saying you replace this with its children, and you evaluate this. So in chess, you're going to have quite a bit. So I'll just do it like this. So you're going to have a bunch of children, and you sort this based on some heuristic information. Sort by some evaluation. So you make a preliminary evaluation, and you have it sorted so you have the best move first. So you've already looked at all the possible moves just at one level deep. In this case, since it's depth first, you're not looking at all your possible moves. So there may be a whole bunch of moves that you haven't looked at. So for example, in this case, if you had a bunch of choices, let's say 10 choices, it's possible that it would have only looked at one of them, and it's pretty arbitrary which one it is. So it's not going to be making good moves at all. It would look pretty much like random moves. So in this case, you're evaluating the children nodes, and the highest one gets moved to the front. So now you know that this is the best node so far, and you take a look at its children. So you take this out of the list, and you split it into its children, like so. Okay, so now you have 4 nodes to look into, and then you evaluate each of those. And you do the same process all over again, which is you take these 4 nodes, these O's over here, and you sort it again by the evaluation, and now it may be in a different order. And this time it may determine that this one is the best. And so it'll start searching from here. Okay, let me just change this to this so that we have room. So now it searches this one, like this. So the way the A-star algorithm works is by looking at the best choice so far and keep drilling down. So this looks like it's possible that this would have a better strategy than the minimax. So let's try to implement that. Okay. So the first thing we need to do is find an evaluation. Let's just go into the code. Okay. So in the code, we're just going to write a function called, let's just put it at the end here, evaluate. And let's just evaluate this position. And let's think about this. We can evaluate this position by taking a look at the piece count. So score is equal to 0, and we're going to add 1. Actually, we're going to add the we count all the rooks, and we multiply it by 5 because rooks would be worth 5 points. Okay, so then let's see: rook, knight, bishop, queen, king, pawn. Okay, and the knight would be worth 3, bishop 3, queen 9. Let's not evaluate the king because the game ends if you'll always have a king. Okay, pawn is going to be just 1 point, so I'll just put a 1 here. So I'm going to duplicate this and change this to minus because we're going to look for the lowercase version, the black pieces. So, and then we return the score. So this is our evaluation. The next thing we need to do is, well, we have the list of possible moves. So given the possible moves, we can generate a new position out of it by duping it and making the move. So we have a way to get its children. So let's actually make that into a method. So def children. And that would take a look at the possible moves, map it. So the index we have actually it's a we have from and to. Okay, so for each one of those, we're going to dupe the current position and make the move. From to. So there's actually a problem with doing it this way. The problem is that, let's take a look at move. In move, there's a possibility that it can raise an illegal move. And that's because it does some additional checks, like, well, actually in this case, the check, it checks to see if the king is in a good position, meaning like it's not a check. Okay, so we have to make sure that we handle that. So we can put this in a begin and rescue. So if something happens, then we'll just say it's a nil. Okay. And so if there's a possibility of nils in here, we'll do a compact to get rid of the nils. All right, so then we'll actually dupe it, make the move. The other thing is that move doesn't handle this form of arguments now, so let's just modify that. So just save this, and this should cause an error. Oh, this didn't cause an error. Oh, because we didn't do any testing for children. So let's see. So children. Okay. Let's see. We have evaluate. We have children. We just need to make sure that this works. Move from to. So let's just do that with the rook. So that's part of move, which is right here. So, okay, 2 args. Rook on e4. And we expect, oh, and then we do a move. Move from e4 to e2. And this should be equal to, it should be the same thing as a new rook on e2, but now since you've moved, now the turn is black, and the half move is incremented by 1. Okay, so let's see if this passes. We're missing a paren or something. Here it is. Okay, wrong number of arguments, 2 for 1 for move. So let's fix that. All right, so let's just say that it's args. If args is equal to 1, then string is going to be the first argument. Else the list string is going to be just empty, and the list is where the from is. So the from would be the first argument, so args 0, and the 2 is going to be the second argument, and we also need to specify what the piece is, and the piece is wherever the from. Okay. All right, I think this should be enough to make this pass. Because the whole point of this big if statement is to set up the list, to, and piece. There are some additional moves, but we'll need to handle that. We'll handle that separately. Okay. Undefined local variable method from. $128. So 128 is right here. Oh, it's list 0. Okay. Undefined method plus for nil class. Okay. Oh, the reason why is because there's no king. So let's modify this so that let's modify in check. Okay. So in check, we'll do this. Check. We'll return false if is nil. If the king position is nil. If the king doesn't exist, we'll say it's not in check. Okay. All right. So the reason why we get this error is because we're comparing two positions together, and we don't have the equal equal. Okay, so we need to create this, and it'll be basically the same as this. So I'll just copy that, except that the equal is equal equal, and we need to go to the end and actually change this to and. Okay, and the last one we don't need, so we just do this. So let's see, the board, and we don't need to say dupe, so get rid of all the dupes. Okay, no more dupes in the king. Other king, so actually for the king we don't need because that's calculated from the board. All right, so make sure all of these match. Okay, syntax error. Okay, let's see if, oh, because of the and. Okay. All right, so everything passes, so that's good. So that means that the possible moves, the 2 argument looks good. There are some problems because along with this, there are cases where you need to make an extra move. So, like for example, castling and en passant. So let's not worry about that for now. Okay, let's see. So we have evaluate, we have the children. Okay, so okay, there's actually, okay, so actually let's do worry about the castling now because that affects possible moves. So there are some problems with possible moves. Okay, so let's put this so that I'll put some carriage returns here so that it doesn't look so bad. Okay, so this looks a little bit better, and I'll do the same thing for this, for the bishop. Okay. All right. So, okay, so let's think about this situation um, about, okay, let's handle the castling situation. And we'll have a king on e1 and a rook on h1. And we'll say possible moves. Let's see. Okay, so let's see. And for now, let's just say that it's empty and see what happens. Okay. It's kind of hard to see, so uh, what I'm going to do is I'm going to say map. We have the from and to. And so I'm going to do from to square and to square. So this way we can read this a lot easier. Okay, so let's see. All right, so we can see that e1 is where the king is, so these are all the king moves. So the king is able to move to d2, d1, e2, there's f. So let's sort these. So we can do this systematically. All right, so we have all the e moves here. So these are the king moves. So there should be 5. So 1, 2, 3, 4, 5. And the rook is able to move, so this is good. So this is one of the problems with this, which is that it doesn't have castling. So we have to include castling. So let's see why this happened. Okay. So for the king, you can see that all these locations are just regular king moves, but it doesn't have, let's see, it doesn't have a castling move here. So let's just abstract this away so that we can see. Okay, I think we can actually, let's see, find piece. Okay, so for this, we need to separate this into capture moves and motion, because when you're castling, you can move into a castle, but you can't capture. So there has to be some conditions, and there are other conditions as well. So there's going to be a bit of logic in here. So let's see. For the king, everything else can remain the same except for the pawn, but the pawn is kind of special. So for the king, we also need to do other stuff. So we're going to break this up. So this is going to be the initial list, and then we have to see if castling is allowed and is the path looks clear, then we should include it. So let's think about how this would look. Okay, so if okay, so first for the castling, the king has to be on e1. So if the, let's see, 2, oh, this is 2. So that this 2 would mean that it would have to be on g1, and the king is located on, let's see, the king of, okay, so you're looking for a white king, so it's based on the color of the piece. Okay, so color of the piece. Actually, I don't know if I have it done this way or piece.color. Let's see. All right, so let's see. Okay, G1, and this exists. Let's just say king index is equal to this. And the king index is on E1. Okay, so actually we have to say, this is interesting because the person's turn, when we first wrote this code, we said that this is based on the piece's turn, not the piece's color, and not the turn, because we also need to do in check, and so that's based on we need to do find based on the piece. So okay, all right, so find based on the piece. All right. So the one thing that we need to say is that the to location, okay, before we do this, we have to make sure that the board to location is empty. Okay, so this is not part of an attack. So this won't be used for the king check. Okay, so this is good. And we'll just put an if statement around here. All right, so then if the board, the to location is nil, with a question mark, so now we can just do it based on the turn. All right, so the king's index based on a turn. All right, so G1 king index. If it's white, then it's E1, otherwise E8. Actually, this one's same thing. So white is G1 or G8. This is a kingside castle. Okay. All right, so then let's just include this. Just keep it simple. So list actually, let's just create a from equals, actually, king index. Oh, we don't even have to, we could just say instead of saying white E1 or E8, we can say king index because that's the same. So, all right, so that's good. All right, so we have a lot of problems here. We're probably missing, oh, we're missing an end. Empty for nil class. So let's see where that's thrown. 134. Okay. For nil class, empty. King turn. Oh, I think I know why. Okay. So it's because of find. Find needs to return something, so returns the list. Okay. All right, so illegal move, king f1. Okay. King f1, it said it was an illegal move. Oh, because there are two choices, e1 and e1. Well, that's interesting. Um, let's see why. Oh, that's because E1 would be here, and oh, we have to specify that to F1 that this is going. Oh, we didn't specify that the 2 is equal to, so that we didn't put this Boolean condition there. So let's see. Okay, so much better. All right, so let's take a look at this. Well, it passed everything else, and this we deliberately left empty so we can just cut and paste this. So, and we can just take a look at the result, see if it makes sense. Okay, so let's see. All right, so we see that okay, in this position, this is very hard to read, so let me just put some carriage returns in here. And put some carriage returns here. Okay, so so the king is able to go into 5 positions, 1, 2, 3, 4, 5, but it also includes E1 to G1, which is the castle, which is what we wanted. And then you have the rook going to E1, H1 to E1. Now this should not be included because that would be taking the king. So that should be excluded. But I think this is a good point to stop because it's getting close to, well, it's over an hour. So we'll pick up from where we left off in the next session.